Okay, everybody. Sorry for the delay. The lighting isn't working for some reason, and I think it's going to screw up. It's probably going to screw up some of the videos I'm going to try to show, but hopefully it'll work okay. They're sending a technician in who's hopefully going to be able to shut at least these front lights off. So this lecture is going to be a little bit of a detour from what I've been doing in the course. So the trajectory has been, we kind of started small with the Earth, and then we're moving out gradually. And at this point, we've basically gotten to the entire galaxy. And I've started talking about the discovery of other galaxies. But over the course of the last few days, there have been a number of events happening in the night sky that have prompted me to talk a bit about asteroids. So you probably got the email that I sent out to the class a few days ago, alerting you to this kind of crazy meteoroid event that happened in the Ural Mountains in Russia on the 15th. And it just so happened that it was on the same day that we were expecting a very close pass-by to an even larger near-Earth object that came very close to the Earth. And a few people sent me emails back asking me to talk a bit more about these kind of asteroids and near-Earth objects. And it is an interesting subject, so I figured I'm allowed to talk about whatever I want to in this class, so I'm going to talk about this. So this is an image of this. Who saw videos of this stuff that was going on? Yeah, it was sort of crazy, right? So this event happened on the 15th at 9:30 a.m. local time. And I think this is probably the first event of its kind that was documented with in the era where basically everyone has a video camera in their pocket. And especially in that area of Russia, apparently everybody's driving around with video. Somehow they're all driving around with videos on their cars. I had no idea that that's what they did. But then this stuff got launched all over the internet and through social media like it was just broadcast around the world. So what this tells you, by the way, is that anytime you hear stories about some crazy sighting, that people are seeing some unexplained phenomena in the sky, and there's not a video of it, you need to be a little bit suspicious, because when something for real crazy happens, like, it's documented and it's all over the place. So what we think this was is we think this was an object falling into the Earth's atmosphere. The thing was about 17 meters across, roughly, we think, when it first fell into the atmosphere. Okay, so that's very large, 17 meters. That's bigger than this room, for sure. And it's like the size of a house or something coming in. And this thing weighed something like 10,000 metric tons. So that's a metric ton is 1,000 kilograms. Now on the same day, 16 hours later, we had a pass-by with a massive satellite, a massive asteroid that was forecast. This, as I'll talk a bit about, this thing, which is called 2012 DA14, was discovered about a year ago, in February actually, by some Spanish astronomers. And it was immediately realized that this thing was going to get close to Earth. But based on the initial calculations, there was really no fear that it was going to hit the Earth on its first passage. But they knew it was going to get very close. And this is one of the recent very close passages with something large. And what people were concerned about is that eventually it might come back and hit the Earth at some time in sort of a century's time scale. It's orbiting around, and it might get close to the Earth in the future. This thing is 45 meters in size, approximately. And it weighs something like 130,000 metric tons. Okay, so if you just, this is 10 times, if this thing were to hit the Earth, it would be a 10 times bigger explosion than this. Now, objects of this size, this thing right here, mostly there's braking from the atmosphere, as I'll talk about. And so this thing deposited, it had a lot of energy, but it deposited that energy primarily in the atmosphere. And then there was a huge sonic boom that ended up blowing out windows and stuff. But fortunately, that energy was deposited up high in the atmosphere and didn't get deposited when it hit the ground. Something this size would probably make it to the ground. And therefore, you really don't want to be anywhere near that when that hits. Finally, there's another famous event of this type that we're pretty sure happened about 65 million years ago. It slammed into the Earth in a sea basin right off the Yucatan Peninsula, we think. And this thing was 10 kilometers in size. Okay, so this thing that you saw the movies of, 17 meters. 10 kilometers. Okay, so here you're talking 10,000 metric tons. Here you're talking about 10 to the 12 metric tons. This is the event that we believe caused the extinction of the dinosaurs. The last, well, the last very major extinction event that we've had on Earth. Although there have been other extinction events, but this was the last really big one we had on Earth. This would have caused massive tsunamis. It would have, thrown up all kinds of stuff into the atmosphere. We think it caused significant wintering because it blocked the sunlight from all the stuff that was thrown up in the atmosphere. So these are big-time bad things that can happen. And events of this type are known to happen in the solar system, we think approximately once every 100 million years, as I'll talk a bit about. So the sort of movies like this one right here that inspired the that inspired all this, one of these dashboard cameras. So you see, for a time, this thing got as bright as the sun. And what you're seeing is this track of this meteoroid coming in. It's braking. It's coming in really fast, much faster than the speed of sound. And then it's braking by the atmosphere. And this braking transports all kind of energy. It heats up the object. And then you get this effective airburst, this explosion that's very, very loud. I'm going to turn the sound off because the best thing is the music these people are listening. And then they just keep listening to it. It's really funny. And so this is another nice image of this thing. So I assume people seen this one. How many people have seen this one? Yeah, so it's pretty. And I've listed somewhere here. I have a website. There's a website where they're uploading all kinds of stuff that people around there were taking images of. It's pretty impressive. So one of the things that you notice from these videos is this thing actually broke into pieces. So it came in as a fairly large rock, but as part of the braking, it broke apart. And so you see these multiple air trails. The other thing that's pretty amazing is there's this tremendous delay from people who are fairly far away. Obviously, this thing's up high in the atmosphere. There's this tremendous delay between when you see this thing go by and this huge smoke and bright thing. And then there's this delay of order a minute, and then all of a sudden you hear the sonic boom. It's extremely loud, and it just freaks everybody out. It just scares the hell out of everybody. And it's quite powerful. So, and it's this sonic boom, this release of energy that propagates out and broke all kinds of windows and thousands of buildings around the area. And it's that breakage of things, that rattling, that ended up injuring a number of people. So here's one of the really cool movies. None of these two get hurt, but this is then hanging around right before this happens, and that's the blast wave. So there's some far distance away from it, and it just comes and knocks the window out, and they feel this tremendous gust of energy, and it knocks them down, and then they run out. Can you imagine? It's so scary. So yeah, I like this too because they're just so casual, just kind of talking, and then right here you'll see it hit. The door blows open, they both get knocked down. I kind of like this one too because he kind of makes sure she's all right before they run. But there's other movies you can see where people get knocked down and they're just they don't care at all about their friends. They're just I'm out. So anyway. So the energy produced from this thing, people are still trying to get estimates now, but safely the energy released is somewhere between 50,000 and 500,000 megatons of TNT. So that's equivalently sort of 3 to 30 times the energy deposited in the atomic bombs that were dropped during World War II. So these are very powerful events, even from the 17-kilometer object that fell in approximately. And like I said before, most of the energy here is deposited up high. And so it has to propagate out before people feel effects from it. Yep.
So the scientists were aware that this one was going to come when in Russia?
No, no one knew this was coming.
Oh, so none of our telescopes saw this one?
No. We would have warned them probably if we would have known. Yeah. No. See, this is kind of part of it, right? There's a huge margin of error, right? We don't know. These things are small, okay? So finding these things is not easy. Thanks. So finding these things is not easy, especially something that's 17 kilometers across. I'll talk later about, oh, what, now it works? I'm so sorry that you had to come out just for this.
Yeah, it's just, let me show you where it is.
I know where it is, I just, for some reason, it didn't work. Yeah,
So.
yeah, thank you. Sorry.
Is this okay?
That's perfect.
Okay.
I'm sorry you had to come all the way here. That's why they pay you the big bucks, right? To the,
Job security.
yeah, right? Thanks, sorry. Yeah.
Were the two events related?
No.
The really big?
Yeah, that's what I'm about to talk about. So immediately when this happens, people begin to think, oh, these must be related because there's two events that happen at once. Okay. So yeah, and I'm getting to that now. Let me just stress that again, taking this question. We did not know this was going to happen. Okay? And we do, even the thing that came by that we knew was, that was much bigger that was coming by, we don't know where all of those are either. So it was kind of a big deal when it was found. Okay, so we're still finding things that are even bigger than this. Okay, so it is kind of an important subject. There's lots of things this size out there. Now the frequency with which these things hit, as I'll talk about later, is like probably once every 50 years, we think. And most of the time when these things come in, they come in over the ocean because most of our land mass, most of the surface area is ocean. So if this would have happened over the middle of the ocean, we wouldn't have known about it, right? The only reason why we know about it is it happened over this city, you know, this fairly populated area where everybody had their cameras. Okay? So it landed rather softly and produced this very circular shaped hole in a frozen lake. About 10-meter wide hole it produced, just from the fragments that were left. Now the fragments of this thing were tiny that were left because they're constantly sort of being disintegrated as they're flying through the atmosphere. These little sort of 1 centimeter size pebbles are what's left, and these things were found strewn around the crater, or this hole. I don't know if you would call it a crater. It probably did not leave a significant crater in the bottom of this lake, although I don't know. So anyway, this is where it's landed. They're pretty sure this is where it landed. Now, as I was saying, this thing got instant fame because it was all over social media, right? So this is kind of an interesting event, right? So this is kind of an interesting event because this is like the first time this has ever been, you know, broadly distributed all over the world. These are my two favorite ones. So at the same time, on the same day, there was another thing coming by. And this thing was called Asteroid 2012 DA14. Don't ask me why. That's the naming convention that they have for asteroids. This is not a real image of it. We can't take really nice images like this of most of the asteroids. This was imaged by a close passage to a similar to another asteroid, but it probably looks something like this. It was discovered in basically a year ago by some astronomers in Granada, Spain, where there's an observatory. This thing weighs something like 130,000 metric tons, as I said before. And at the time it was discovered, it was understood that there was a small but non-zero risk that this thing might eventually hit the Earth sometime this century. And given that this thing is about 10 times more massive than the thing that caused that airburst that we just showed, you get a little bit concerned when you find these things, and you want to make sure that it's not going to hit. And I'll talk a bit about what you would do under those circumstances. Right now, if we had discovered this thing was going to hit the Earth, basically all we could have done in a year's time, given what we have right now, is probably just evacuated the city. If we did a very precise calculation, figured out basically where it was going to hit and what time, probably the thing we would have done is just evacuated that area. Because you need a long lead time to do anything about these objects. So, but I'll talk a bit more about that a little later. It was known at that time that it would come very close to the Earth in February of 2013, the thing that just happened, and it was also known that it wasn't going to hit us dead. Okay? So we knew that it was going to have a near-Earth passage in about a year, and we also knew it wasn't going to hit, but it was going to be interestingly close. And this is how close it came relative to the size of the Earth. And it did. It got to within 34,000 kilometers. So again, on the same scale, this is basically the size of that Ural Mountain meteor. And this thing got kind of uncomfortably close. So what happens when something like this hits? These things have hit the Earth before. Let me give you an example of when a 50-meter size object hits the Earth. Makes something like this. So this is the Barringer crater in Arizona. It's about 1,200 meters wide, and it's 170 meters deep. So if you go out sort of near, I think it's near Flagstaff. Maybe someone knows. You can go out and see this. I've actually never seen this. I'd love to go see it sometime. We think the impact happened approximately 50,000 years ago.
Did the asteroids themselves always disappear?
No. So there would have been a meteoroid left probably from this object, from this crater.
But we don't know. Right?
The big one. I am not enough of an expert on this to know if that meteoroid was found. Yeah.
It was found.
It was found.
In like their
In the visitor shop or something?
Yeah, visitor shop, and there's also one in California.
Okay, how big is it? Have you seen it?
It's like the one I saw.
Yeah.
I saw 2 of them, but it's like this big.
From Barringer crater?
Yeah, there's like 2 of them.
Okay, and they're like this big.
Yeah.
And they're
there's like
basically.
2 around the world.
Okay, yeah. Yeah, you definitely can see these meteors that are left over. And you can see them. And you can go to museums around the world and see these things. And they're really impressive. And oftentimes they're very dense things because some of the things that are left over are very rich in metals, and so they're extremely heavy. And they tend to have compositions that are quite a bit different than most of the compositions of stuff on Earth. So it's very easy to tell them. So one great place to go find these things is up say in the poles, where you're just out over white ice, and then you just see these kind of black rocks sticking out. So that's a great place to go look for these things. And some of the first people to go do these treks to the South Pole, like one of the scientific things they did is just sort of collect these meteorites that they had found and then try to bring them back for analysis. So yeah, you see these things, you find them all over the world. So they've definitely hit before. And apparently this one was actually found and was known and is in museums. So the California Science Center has one too? All right, cool. So this kind of thing happens. When they happen, they do big bad things. And I'll talk a bit about this later. The most recent kind of big thing that's hit the Earth that was bigger than this Ural Mountains event that we just saw is sometimes called the Tunguska River event. The Tunguska River event happened in 1908, also in Siberia. So this was the Soviet Union, and not also in Siberia, in Siberia. And this was sort of at the beginning of the Russian Revolution, so there's a lot of stuff going on in this area at the time. So this was also an airburst event, and it released probably 10 to 15 megatons of TNT. So this was a big thing. So again, that's at least 10 times bigger than the thing, well, let's see. Yeah, at least 10 times bigger than the thing over the Ural Mountains. Eyewitnesses reported feeling the heat blast and ramifications of this thing 50 miles away. And the sonic boom from the event was recorded, 1,000 kilometers away. So there were seismographs available at this time. It was probably about 40 meters in diameter. So similar, maybe slightly smaller than the thing that we had the close flyby with. And it possibly actually was a comet and not an asteroid. And I'll talk a bit about what the difference is. That basically means it came in from farther outer part of the solar system, was probably moving faster than the asteroids typically do. And we think that an event like this should happen once per 100 years. Something like that is the cratering event of things like this. And yeah, so this recent airburst was at least 5 times less energetic. think I got the number wrong there. Probably at least 10 times less energetic. And you know, this happened in 1908. We think events like this should happen once per century. Maybe the Ural Mountain event is our effective Tunguska event. Maybe not. So maybe there's another one that's going to come like this. But these are big things. It knocked down trees all over the place. This was a pretty unpopulated area, thankfully. So as far as we know, no one died, or maybe one person died. But it sort of wiped out forests for very large areas. And you know, this is also a topic of like people talk about like UFOs and stuff. There's always sort of like conspiracy theorists, people who like to make this out like it was some kind of mysterious thing. But it's quite well understood that the most plausible explanation for this event was it was basically one of these asteroid strikes of the kind that we know happen. And everything that happened is consistent with those kind of events. So someone asked me about this earlier. So here is the trajectory of that Russian meteor that hit, that we saw the movies of. And this is the trajectory of that AD-14 asteroid near flyby. So, you know, immediately it's kind of weird that you have these two kind of space rock phenomena happening on the same day. But we think that they were completely disconnected. It was just sort of like a random chance. These objects are moving so fast, the fact that they were separated by 16 hours means that that in terms spatially, they're really spread out. And on top of that, they're coming from opposite directions. So it doesn't seem like they're really related in any way. Now, we didn't track this thing all the way out here. We only saw it in here. So, you know, maybe some kind of crazy something happened where it was coming along this way and then got sucked in this way. I don't understand how that could possibly happen. The most plausible explanation is they were just, you know, we get hit by rocks all the time. Just so happened that two flybys happened about the same time. Again, this is just to scale. This asteroid AD-14, bigger than the space shuttle. This Russian meteor is somewhat smaller than that. So notice that we're calling, you know, there's all these different names that you see thrown around. So this thing was like, you call it a meteoroid, you hear meteor, you hear asteroid. What are all these things and what are the difference? The first approximation, they're just kind of rocks coming in from space. So that's kind of all we're talking about. But then there are these specific names, and I just thought I would give them to you in case you hear them. Okay? So what's a comet? A comet is something that primarily has ice and rocks on it. And oftentimes, because when those comets get close, they're oftentimes coming in from the outer solar system where it's colder, so they'll have more ice. Then as they get closer to the solar system, you get evaporation, and that's what produces these tails. So those are the things that often have tails. And they're on these plunging orbits. And because they're on these plunging orbits, by Kepler's law, they are going really fast by the time they come in. The asteroids, on the other hand, tend to be orbiting closer to the Earth. And they're on more circular orbits, so they're not going quite as fast. Oftentimes, most of the asteroids that we know about live in something called the asteroid belt, which I'll talk about in a bit. And sometimes, though, their orbits are kind of kicked by the big massive Jupiter that's sort of at the other edge of it. And Jupiter kind of perturbs the orbits and knocks them in to an orbit that brings them in closer to the Earth. So then there are these things called meteoroids. What are meteoroids? You hear that term. Meteoroids are like little small asteroids. And in fact, they're bigger, so they're bigger than dust, but they're smaller than an asteroid. And a practical definition is it's basically something that was too small, that's too small to see until it hits something. So the thing that lit up in the atmosphere is a meteoroid because we didn't know about it beforehand, and we could have never seen something that small. It would have been hard to see something that small beforehand. That's one way to think about what these meteoroids are. Now a meteor is when it's bright in the sky. So that's the thing that flashes. So a meteor is like a shooting star. It's the same thing. And finally, a meteorite is the solid thing that you find on the ground. All right? Now, I don't care in detail that you actually know the precise differences between these things, but I'm just giving it to you here just so you've heard it. I often confuse them and probably say the wrong word half the time. Basically, it's rocks coming in and hitting the Earth. Yeah?
Is it possible for an asteroid to knock the moon out of orbit?
Is it possible for an asteroid to knock the moon out of orbit? If it was big enough, it could. But we are not aware of anything that large. So it would have to be really big. It would have to have a lot of energy to knock the moon out of its orbit. And there's nothing plausible that's going to be doing that anytime soon. Asteroids are related to the moon, as I'll talk about in a bit. Way back, okay, there's a rate at which these things are hitting the Earth all the time these days, right? But if you go back, remember the Earth's about 4.5 billion years old. So if you go way back to when the Earth was only about 1 billion years old, during that first billion years, the Earth is being hit all the time by really, really big things. Bigger than any of these kind of things that I've talked about yet. Like 100-kilometer size things. And that was doing all kinds of sterilizing the Earth repeatedly. Just huge, massive impacts into the Earth. If you go back even a little bit farther, we think about 4.5 billion years ago, about the time the Earth itself was forming. We think that the Earth slammed into something that was about the size of Mars. So about 3,000 kilometers in size. And during that collision, something broke off of the Earth. And that thing that broke off is the moon. So the moon, we think, actually formed as a result of one of these crazy big collisions that happened a long time ago. So this is another one of this is kind of a nice sort of video that was put together by folks at AGI, I think basically to advertise their software, that gives you a map of what we think happened. So this is that Russian meteor coming in. And that's its trajectory compared to the trajectory of this AD-14 asteroid that came nearby. What are all these things? Those are near Earth, those are basically Earth orbiting satellites. So that track that asteroid came in, actually, not only was it closer to the Earth than the moon, it came in too within the geosynchronous orbit of satellites. So there are a lot of satellites that we launched that are orbiting outside that sphere that the asteroid passed through. And I'm not aware of the asteroid hitting any of those satellites. I think it was quite a distance away from the satellites and never was in danger of hitting them. But in principle, it could have on its way in. It's also possible that it hit some satellite that we're not supposed to know about that's orbiting around there, these geosynchronous satellites. Geosynchronous means that they stay in the same place relative to some position on the Earth. So as the Earth turns, they orbit with that position. So they can just point right above your house and stay there forever as the Earth orbits. As the Earth spins, sorry. So I wanted to talk a bit about the energy of these impacts, because this is a nice opportunity to talk a little bit more about energy. Another form of energy that we haven't talked that much about is called kinetic energy. So you have something with a mass and it's got some velocity. It will have energy associated with that motion. So kinetic energy is equal to 1/2 times the mass of the thing times the velocity that thing has squared. So what that means is the more massive you are traveling at a given speed, the more energy you have associated with that motion. And the faster you go, the more energy you have. And in fact, if you double the speed, you have 4 times as much energy of motion. Now, this is the basic equation that we need to understand how much energy these rocks have when they're coming in. And from this, and this alone, you can understand a lot of the stuff you heard reported on the news about this kind of stuff. So one of the things is the velocity. The velocity, we kind of know what the velocity, roughly what the velocity should be. The velocity of the Earth going around the sun is about 30 kilometers per second. So that's a typical speed of something that's at 1 AU from the sun that's kind of in orbit around the sun. It's going to be about 30 kilometers per second. So that's a characteristic speed for these space rocks that are right around the Earth. Now there's some slop in that, because really you care about how fast it's moving with respect to the Earth, and not all the orbits are perfectly circular. But let's just say somewhere around 10 to 100 kilometers per second is the speed with which these things are flying around out there and are going to hit the Earth with. The masses, on the other hand, can have a huge dynamic range. There are lots and lots and lots of objects going around out there that are like 1 meter in size, that weigh about 1,000 kilograms. And the largest asteroid-type objects known are like 30 kilometers in size or so. And those have masses of 10 to the 17 kilograms. So you see, the first thing you care about when you want to figure out how much energy these impacts are going to deliver is more or less how massive the thing is. We are scared of the big ones. Right? You do not want the big ones to hit. Because the velocity is not changing that much. It's the mass spectrum that we're worried about primarily. So let's figure out roughly where some of these numbers came from. So imagine we think about something that's going 10 kilometers per second and has a mass of about 10 to the 7 kilograms. That's roughly this Russian meteoroid that we're talking about. So we can plug those numbers into this equation. 10 to the 7 kilograms, 10 kilometers per second for the velocity. You square all that stuff out, it turns out that the joule has units of kilograms, kilometers squared per second squared. So you multiply all these numbers together and you get something in joules. It's about 10 to the 15 joules. All right? So that should be an approximate sign. And 10 to the 15 joules is something like 240 kilotons of TNT. If you think about this in terms of explosive power. And that's about 10 times more powerful than the atomic bombs dropped during World War II. So that's where that comes from. But again, this thing deposited that energy up in the air because there was enough braking to happen up in the air that it deposited basically into the atmosphere, and that created this blast, this sonic blast. Let's do a second example now, something that's kind of like the AD-14 asteroids. I played with the numbers a little bit. This one I have going at 30 kilometers per second, but its mass is about 10 times bigger, about 10 to the 8 kilograms. If you work these numbers out, you get something like 10 to the 17 joules. And that's 24 megatons of TNT. So if this thing, something like this, were to hit the Earth, this is equivalent to the most powerful atomic device that we've ever built and that has ever been detonated. So the Russians did this, maybe the Soviets at the time. This is an actual image of this detonation. It's called the Tsar bomb. It had roughly this kind of energy. This is a 35-mile-high mushroom cloud. And the power of this explosion is so great that it would give third-degree burns to people 60 miles away. So these are quite dramatic events. And fortunately, I think, hopefully, all of the bombs of this type have been destroyed at this point. But this is kind of the most powerful thing that humanity could possibly do. Harnessing all of the power that we know about from atomic energy, we can create things, that have this kind of energy. This is not that crazy outlandish of an asteroid. In case you're interested in this stuff, I found this website that's kind of fun at purdue.edu, which is just called Impact Earth. And you can put in things. You can say, well, I want to see what would happen if I have an asteroid moving this fast of this mass that hits here. And they calculate things like, okay, how big would the tsunami be if this thing hit, etc. So if you're interested in this stuff, this is kind of a fun website. So as I mentioned, it's the size of the asteroid that seems to matter the most, right? So let's talk a bit about the size of these asteroids. This is DA-14, 50 meters across roughly, impact energy of the most powerful atomic device that we've ever built. This Mount Ural meteoroid is much smaller on this scale. Again, these are to scale. And this would be, again, you saw the movie of what happens. The difference is something like this would probably hit the ground. This thing would probably be depositing significant energy on the ground, whereas this thing deposited up high in the atmosphere. This is one of the bigger asteroids that we know about. It's called Gaspara. This is imaged by the Galileo spacecraft. It's 15 kilometers across. It's 50 meters, it's 15 kilometers. 10 to the 16 kilograms. But these two images are not to scale. Okay, so let me show you them to scale. Something this size can create an impact that's as powerful as the most powerful atomic device we've ever built. So the volume, and the masses of these things scale like the volume, not the size. Okay? So even by eye, this looks, many times bigger, and then you cube that difference, and that's the mass. That's how much energy difference would be delivered in these impacts. Now, fortunately for us, this particular thing is tucked safely away in the asteroid belt. This thing seems to be on a fairly stable orbit, and as far as we know, it's not headed our way anytime soon. What is the asteroid belt? The asteroid belt is basically where all the asteroids are, mostly. So it's this belt of asteroids that live basically in between the outermost rocky planet and Jupiter. So it's in between Mars and Jupiter. There's this belt of asteroids that go around. So this is kind of a pretty picture that characterizes what's going on. Here's the main asteroid belt. Then there are some other asteroids out here. They're called the Trojans, asteroids that sort of follow along around Jupiter. We think there's about 1 million asteroids in the asteroid belt bigger than a kilometer across. But there's only about 100 bigger than about 150 kilometers across. We think. So the asteroids that live in the asteroid belt don't scare us that much as long as they stay in the asteroid belt, because they're out there. But you'll notice in this plot, there's some dots here. Each one of these dots, I should mention, is just been put there by a computer at the location of an asteroid. You shouldn't get the impression that the space is very dense in asteroids, though. The spacing between asteroids is really large. So it's not like that scene in Star Wars where they're flying through an asteroid belt and they have to weave in and out. The distance between asteroids is big. So if you had an asteroid that was the size of my fist, that was, say, a kilometer, you took a kilometer-sized asteroid and shrunk it down to the size of my fist, the nearest other asteroid in the asteroid belt would be in another state. So it's not like they're really close together. This is just, it's hard to plot them to scale here. But every now and again, if you're an asteroid that's sort of orbiting around, especially if you're a big one, you got this big massive thing, Jupiter, out here. And Jupiter can give you a little push every now and again. It's big, and every now and then just gives you a gravitational push, and can knock you out of your orbit and send you either maybe careening into the sun, but also maybe kind of alter your orbit so now you kind of come in here. Those type of things that are near the Earth are called near-Earth objects. They're not near-Earth asteroids necessarily, because some near-Earth objects are technically comets or something else. But we generally just call them near-Earth objects. But they have orbits for whatever reason that bring them close to the Earth. And these are obviously the ones we're more concerned about. We know of about 6,400 of these things, but there are probably 20 times more than that are out there with sizes greater than a meter or so. But we haven't found them yet. So what's shown here is a projection, a guess, of how many we've found that are bigger than a certain size. So I don't know if you can read this, but this is objects bigger than a kilometer. We think we know of about 87% of those where they are. So that's not even 100% of the things bigger than a kilometer do we know about them. But it's close. Then you get down to things smaller than a kilometer, and it's like, certainly not that many. It starts dropping off rapidly. There are probably 1,500 near-Earth objects bigger than a kilometer. And the thing that happens is their orbits are kind of unstable. So sometimes they can get kicked in to the Earth's region. Sometimes they go careening into the sun. Sometimes they get kicked out. Sometimes they actually collide with a planet. And then new ones are fed by the asteroid by just being accreted from the asteroid belt. There are lots and lots of people looking for them now. That's one of the goals of some astronomers these days, trying to find these things and figure out where they are. And there's a goal that I'll talk about in a little bit, that we try to find everything bigger than 150 meters in size. Which means we definitely do not know where everything bigger than 150 meters in size is. This is 10 times more massive than AD14 that I talked about. So the goal is even to find things that are 10 times more massive than this recent event. The goal is not to find everything as big as this AD14 asteroid. And certainly things as small as the 17-meter Russian meteor that just happened. We definitely don't know where all those are. That's not even part of the plan to find where all of those are. And the reason why is it's hard to find these things, okay? How would we find them? Well, they're kind of these big rocks and they reflect light from the sun. But they're not that big. They don't reflect that much light, and a lot of times they're kind of far away. So how do you find them? So it's not that easy. So you look for little faint things that are moving fast compared to the background stars. That's kind of how you find them. You look for things that are moving anomalously fast compared to the background stars. But they're very, very faint. So let's do an accounting here. So here we've got, oh, let me back up. So this thing here, this is Eros. This is a different thing. Eros is actually a near-Earth asteroid, and it's 15 kilometers in size. It's Eros' sister probably that killed the dinosaurs. It's something like this. So let's do a little bit of an accounting here for where we're going. So just to sort of emphasize, here's Eros, this big near-Earth object, and here's DA14, the flyby we just had. I'm not even going to put the 17-meter thing on there because it's so small. Its size is about 10 kilometers, 10 to the 4 meters, whereas this thing's size is about 45 meters. Now, the important thing is its volume, the volume of something scales like its size cubed. So the volume is going to go like d cubed. So the volume of Eros is going to be something like 5 times 10 to the 11 meters cubed, whereas the volume of this thing is only going to be like 5 times 10 to the 4 meters cubed, much smaller in volume. Now, most of these things have about the same density. They're kind of made of rock. There's variations, but let's just guess something like the density of rock, which is 3,000 kilograms per meter cubed. So you have a meter-sized rock, it's going to weigh about 3,000 kilograms. All right. So you can then estimate how massive these things are. This thing's 10 to the 15 kilograms. This one's only 10 to the 8 kilograms. So it's this kind of scale in energy that we're talking about. Now, we know that big things have hit the Earth in the past. I already showed you Barringer crater. This is the Wolf Creek crater in Australia. We think it's about 300,000 years old. And it's got this interesting double ring structure that you often see in meteor craters. A lot of the craters on the moon look like that too. There's this amazing circular lake, almost perfectly circular lake in Quebec that we think is basically a collapsed impact crater. This thing we think happened about 200 million years ago. And it's just filled in by all the rain and stuff up there. That's why it's a lake now. In fact, we know of craters like this on all over the world. At least 50 of them are known. They happen in all continents. And the other thing to keep in mind is the Earth's crust is relatively young for the age of the Earth. The crust of the Earth is about 100 million years old. Because there's tectonic activity, there's weathering, all kinds of stuff happen on Earth. So we're not going to find very many things older than this, because the crust of the Earth is sort of like plunged over again. But we do have the moon to look at, and the moon doesn't have all that tectonic activity, doesn't have any weather. And so what you can do is use the moon as kind of like your your gauge for what the meteoring rate, the cratering rate has been over the last billions of years. And the moon, we actually use the moon to get a lot of the statistics we have about how frequent these kind of impacts are. Now, as I mentioned, impacts like this were happening all the time in the past, and there were like 300-kilometer asteroids hitting the Earth all the time 4 billion years ago. And we think that these were sterilizing impacts. Okay, talking about magma seas, just everything was so hot as a result of these very energetic impacts. And this is why we think it took a little while for life really to take hold on Earth. You couldn't really have liquid water during this time because it was so hot. But as soon as it was possible for life to take hold on Earth, what happened is this meteoring rate died down. These big rocks were kind of left over from the formation of the solar system. They got cleared out pretty fast, and then now we're down to this kind of more level, lower rate that we have today. So once all this stuff got cleared out, and we could actually maintain water on Earth, life began to happen on Earth pretty fast. If you go back even farther in time, I mentioned this before, there was something about the size of Mars. The leading theory for the formation of the moon is that something about the size of the Mars slammed into the Earth about 4.5 billion years ago. A piece of it broke off, and that's the moon. So, you know, asteroids have played a fundamental role. These kind of impacts have played a fundamental role in the history of the Earth, going back to the moon itself. And it was only when their rate died down did we start having life on Earth. But if we fast forward now a bit, we think that these impacts may have played a continuing role of life on Earth. And in fact, if it wasn't for the big asteroid that we think hit 65 million years ago, we probably would not be in this room right now having intelligent discussions. So there's this thing called the KT boundary, which is a boundary layer of sediment on the Earth's surface that divides what's called the Cretaceous and Tertiary periods. It's called KT because I guess in German, Cretaceous is spelled with a K. It was the Germans that started calling it KT. But this boundary is interesting because in this layer you see a lot of iridium, an element called iridium, and you see a lot of soot. And you see this stuff, this very anomalous level, 100 times the normal rate of iridium in this layer. You see this layer all over the Earth. Interestingly, this amount of iridium is comparable to what's found in asteroids. Now, about 65, this is associated with the time about 65 million years ago. And at this time, there was actually a mass extinction. A mass extinction where a huge percentage of all the major life forms on Earth were wiped out. 75% of land and marine species were gone, including all dinosaurs that didn't fly. The flying dinosaurs made it through, and they're now like the chickens and the sparrows and the birds. But the T-Rexes and the brontosauruses and all that kind of stuff suddenly disappeared. In fact, there's been 5 major big extinctions in the last, 500 million years or so. But the one I'm talking about is right here at 65 million, where this is sort of biodiversity versus time, and there is this kind of ramping up and then all of a sudden a dip right here at 65 million years associated with this KT boundary layer that I'm talking about. Now you know where I'm going to go with this. One of the leading theories for why this happened is because there was an asteroid strike. And this is why you have this iridium layer. The kind of asteroid that we're talking about would have to have been something like 10 meters across. So arrows, like these big things that I've been showing you. This would be about 2 million times the energy of the most powerful nuclear bombs that we know about. It would have spawned global firestorms. We think it hit probably in an ocean, so therefore mega tsunamis. It would have kicked up all kinds of stuff in the atmosphere, dust, etc., clouding out the sun, making it get cold. So, you know, it doesn't matter how evolved you are to the climate that you have, okay? So if you're a T-Rex and you're not scared of anything, suddenly it gets very cold and there's global tsunamis and firestorms and all the brontosauruses die, you got nothing to eat and you die. It doesn't matter. And then there's some little, you know, rats and stuff or whatever, little mammal things living in the crevices and the nooks that don't need as much to eat maybe. Somehow they're, for one reason or another, a bit hardier. So then they can take over. And after millions of years, the climate settles back down again. You have something that's ready to support, you have an ecosystem that's ready to support bigger beings. The mammals began to take over those niches. So that's the idea. Yeah.
I just want to go back to the moon. If the moon broke off from the Earth, how did it become circular, and why in the Earth isn't there like a dent or something?
Right. Okay, I want to go back. So she's been thinking about the moon the whole time, which is great. So the question is, but that sounds crazy. How if the moon broke off from the Earth, why isn't there like a big like Cookie Monster bite out of the moon, out of the Earth, and why is the moon like a sphere? Okay. So when things are as massive as the moon and the Earth, especially when they get hot and deformable, gravity acts to make them into spheres. So gravity will tend to try to make things into spheres if they're massive enough. Now, a lot of these asteroids I show you are not looking like spheres. They look like big potatoes. But that's because they're not massive enough to be spheres. When you get to a massive enough thing, okay, like Mars, that will become a sphere. And so the reason why why the planets are spheres is they're just massive enough for their gravity to make them spheres. So the basic idea is you have this tremendous impact, a lot of energy, things get really hot, that sort of makes it into sort of more of a liquid type molten state. And the moon breaks off from that and it's kind of an oblong funny thing. But then once that kind of settles down, then the self-gravity takes over, everything reshapes into a sphere and you get this kind of long-term solution that you have now. Certainly right after the impact, there was not looking like a sphere. It was, you have to wait a long time, thought the sphere. So that's the idea. Any other questions? Yeah.
If something big enough to kill us, or at least kill most people, was headed for us, do you think we could do something about it?
I'm getting to that at the end. I know that that's where I'm going. I'm trying to scare the hell out of you, and then I'm going to tell you. You're thinking the right thing. I'll get to it, I promise. Yeah.
What causes the different orbits of the asteroids and the comets?
Well, that's a complicated question. The question is, what causes all these different orbits of the asteroids and comets? You know, it's pretty stochastic out there, all right? So imagine you have a family. One way to think about it is there's lots of different orbits that things could orbit around the sun. The ones that are the weirdest and craziest tend to get perturbed and kicked out. So the ones you're left with are the things that are nice and circular. But the asteroids are small and they can get kicked around by these larger bodies. So every now and then if you get kicked a little bit, you can get plunging into these plunging and longer orbits. Fundamentally, why are they there? You know, I think maybe you're trying to ask, like, why are they there? Like, why are they like that? And you know, what's the fundamental reason for it? Basically, I mean, maybe one way to answer it, there's chaos in the beginning. 4.5 billion years ago, there's chaos in the solar system. The solar system's just getting started. Things that are destined to collide, collide. Every now and then, big things run together and you get the moon. Okay? But if you wait long enough, most of that crazy big stuff that's going to happen has already happened. And the only things that are left are the ones that kind of fall in line. So that's why everything's kind of ordered now. We've waited long enough for things to settle down. But every now and then there are these rogue things that happen. There's enough asteroids out there that you can get, every now and then you can just kind of get random perturbers from giant Jupiter, which is supermassive, for example. That you have an asteroid that's doing its own thing, totally in line, going in a circle, but that for some reason it kind of gets close to Jupiter, a little bit too close one day. Jupiter kind of pulls it out, and suddenly it's on a different orbit than it was before, and now it tends to fall in and get closer to the Earth. So it's sort of for reasons like that. Object by object, we don't know. But that's the basic idea. Any other questions? Okay. So the crazy thing about this dinosaur meteor hypothesis is we think that we've actually found the crater. And the Chicxulub crater is located just north of the Yucatan Peninsula, sort of the Gulf of Mexico area. And it's about a 200-kilometer diameter crater that's basically underwater. It was found by people, Mexican and American geologists, who were actually trying to look for oil down there, trying to look for evidence that there would be oil. But they found these rocks that were sort of surprising. They also found a lot of shocked quarks, okay, which you get from things getting shock heated really fast, which is a signature of impact. Impact glasses, so heated, flash heated silicon that then turns into a glass as it falls back down to Earth. And now it's being studied by gravitational anomaly. You drive over there with a boat and you do a gravitational sensor, and it looks like the gravity is somewhat different in that part of the basin. And you can create these maps that really do look like impact craters. In fact, double ring type craters, exactly the kind that I showed you a little earlier today. If you radiometrically date this crater, you get about 65 million years. And so there's a lot of things that are pointing to this specific crater being the crater that killed the dinosaurs that's responsible for the KT boundary layer. So how do all these things stack up against each other? So what we got going on here is, this is the mean interval in years between different types of events. And these are the sizes of the things that are going to hit along this axis in meters. Up here is an approximate value for the impact energy. Remember, I already argued to you that the impact energy basically ought to be given by their mass, because the speeds are basically the same. So the more massive you are, or the bigger you are, the bigger your impact energy is. So let's go down here to this Ural Mountains point. So this thing was about 17 meters in diameter, and it delivers an impact energy of, say, 300,000 kilotons of TNT. And we think events like this ought to happen, at least according to this plot, once every 30, 40 years. All right, so this is where all the movies and all that kind of stuff. That's this guy. This Tunguska event that wiped out all the trees and presumably killed caribou or whatever was going on in Siberia at the time, that was a bigger thing. Okay, so it was living up here. That was probably as powerful as the largest atomic bombs that have ever been detonated or built. We think these things ought to happen once per century or so. Once per 100 years, maybe every couple hundred years. We don't know. There's slop in these numbers. Way up here, this is the 10-kilometer thing that gave rise to the KT boundary and killed the dinosaurs 65 million years ago. So, you know, we have this one to thank for us being here, because it's highly unlikely that mammals would have taken over, that humans would have risen up like we did if there were still dinosaurs ruling the earth, right? Now, maybe we'd be all real intelligent lizards or something, but that's not at all obvious to me. So anyway, there's this. Now, what's color-coded here is the kind of destruction you're talking about. So the green is local destruction. I mean, it's not good. It's not like you want to get hit by one of these things. You don't want your office building to have its glass blown out. But it's not like it's going to end the world or anything. And then, you know, you start getting up in here, and it's sort of regional devastation. You might wipe out a city in the surrounding areas. And then once you get way over here, you're talking everything on the planet is extinct. So I've heard astronomers classify things this way, so I thought it's kind of fun to say this. So you can have these you can classify these objects, okay? City buster meteors that are 30 meters in size. You expect these every 50 years or so. Bigger than the Ural Mountain events. That's about a megaton of TNT. For these things, it's kind of nice because the atmosphere provides a shield, so they largely burn up and deposit energy in the atmosphere. Then you have the next class of things you can call the people busters, because these things are 1 kilometer size asteroids. They're not really shielded by the atmosphere. The atmosphere doesn't take up most of the energy, so they deposit on the ground. You're talking about 100,000 megatons of TNT in these kind of events. These are arguably global events, certainly hemispheric events. They'll disrupt life, kill a lot of people and animals and species over big portions of the Earth. And then, of course, you have these sort of planet buster things, these 10-kilometer size things that killed the dinosaurs. And you're talking about global mass extinctions if these things hit. Now, these people busters happen every 100,000 years, right? And I showed you a picture of one that happened 50,000 years ago, Barrister crater. There were people on Earth then, by the way, like full-on like people that you would recognize as people. They probably weren't living there in Arizona at the time, I think. But there were people on Earth then, 50,000 years ago. And you could ask, well, that was 50,000 years ago. We only get one every 100,000 years, right? But this is a statistical statement, right? So think about rolling dice. If you roll a pair of dice, on average, every 36 times you're going to get double sixes. But let's say you've rolled the dice 20 times without getting double six. Are you confident that the next time you roll it, you're not going to get a double six, that you have to wait 36 full times to get it? So these are statistical statements. Now, what's plotted here, I'll tell you what it is. You don't have to pay too detailed attention, but this is the cumulative number of things bigger than a certain size. All right, so this is 10 kilometers. This is like killing all the dinosaurs. And over here is Tunguska, and way down here is the Ural Mountains. This blue line is a rough estimate of how many we think are in total out there. And the red line is how many we've found. So the big ones, we think we found them all. We think we know of everything bigger than a kilometer. Meaning that if for some reason it was on its way to us, we would know it, at least. Once you get to a couple hundred meters in size, it's still really big. Bigger than this, biggest atomic bomb that has ever been dropped, energy type things. We don't know about all of them yet. We know we don't know about them. This is like a known unknown, right? And then you get down here, it's like we don't know. There's a lot of them out there. And that's because the small ones are harder to find. So let's get to this question. So any questions about this, by the way? And again, this color code this is like extinction. This is a global event, regional, The color code is with the type of damage that we're talking about. So the US Congress, for example, has given the US Air Force and NASA has sort of made proclamations that our goal is now to track everything larger than 150 meters in size that is going to get closer than 0.05 AU from the Earth. That's the goal. And there are projects that exist and that are being planned to do this. This figure was made by a telescope project called LSST, which is going to scan half the sky every 3 nights. And one of the science goals of LSST is to find these near-Earth asteroids or near-Earth objects. And UC Irvine is a partner in this project. But it's not done yet. And let's say something was found. Let's say, so via one of these methods, there's a number of searches of these things going on right now. Let's say we find something. It's pretty big. It's coming our way. You go back with better telescopes, confirm, yep, it's going to be here. It's going to be here in some number of years. What do you do? Well, there's a couple of different ideas. So let's just talk about ideas first. Okay, you could send Bruce Willis and an army of, gung-ho people up there, some oil drillers up there to light it off with a nuke. You could try to do that. That's probably not what you want to do. You do not probably want to blow one of these things up into many pieces. Because then what you have is instead of one big thing coming at you, you have like this cloud of, you have a shotgun blast now that's just like the size of the Earth that's just coming at you. Okay, so you probably do not want to blow it up. One of the issues is we don't know the composition of all these asteroids. We don't know how stuck together they are. So if you go up there and try to mess with it, you might just break it apart and now it's in 100 pieces. The total cumulative mass is the same, and it's still barreling at us. Okay, so you don't necessarily want to do that. Now, for objects smaller than about 300 meters, okay, again, which we don't know all of them, if you have an early warning of several years, it would then be possible to send weighted robotic spacecraft up there to latch onto them and then give them a nudge. So the basic idea is, you know, if space is very big and you've got one of these asteroids and you've calculated that it's going to be this crazy thing where it's headed this way, the Earth is moving, and they're just going to ram together. But if you're really far away, you don't have to nudge it much to make it miss. Okay? Imagine trying to make a pool shot from across the table. Okay, you have to be much more precise to make that shot than you do if you're really close to the pocket, right? So, you know, if someone's shooting a pool shot from across the table and you just kind of stand behind them and nudge their pool cue a little bit, they're going to miss. Okay? So it's the same deal. That's why it's harder to make a basketball shot from three-point line than a layup, right? You have to be more precise. The farther, you know, if you're off by just a small angle, you're going to be way off by the time you get there. So the idea is you catch these things really far away and you just give them a nudge, just a little push. You don't have to push them that much, and then you'll screw up the orbit and it won't hit the Earth anymore. So that would be the smartest game plan for how to do this. And we think for the smaller objects, you could do it. Now for the bigger objects, much bigger than that, weighted robotic spacecraft is probably not going to be enough to nudge them, to change their momentum enough to keep them off track. So then you have to think about other things. So you could think about doing a nuclear blast, but you probably want to do it, make the explosion stand off. So you have the thing, it's coming at you, you make it explode kind of here, so you sort of push it. You probably don't want to ram right into it and blow it up, because that would break it up into pieces, and then it's still coming at you, or at least some number of those shrapnels will still be coming at you. The other thing to keep in mind is like about 50% of these near-Earth objects, 30 to 80%, are in orbits that cannot be reached by launch systems that either exist or are planned to exist. So what does that mean? We don't have rockets that can get to them, certainly in a short amount of time. There's just none that exist. So even if you knew what to do, it's not obvious we could actually get something to them. So you would need to do something like have a complicated flyby planetary assist kind of orbit to get them to them. Or maybe build some other kind of launch system once you're in space to then fly these things there. Okay. And of course, that technology does not exist. Most of this technology is not in-house, right? It's not like NASA has like a warehouse of like robotic asteroid deflecting, rockets that they'll just like, oh, okay, there's an asteroid headed this way, okay, we'll go get it. No, not at all. It doesn't exist. So while Congress has recommended, and there is some funding that's been put forth to find these things, if we do find one, it would be an interesting scramble in science policy to figure out whether it's possible to get the thing built in time to actually do anything about it. So, and you might wonder, how is it possible that NASA can't do this? But NASA actually isn't, people have an impression that NASA is funded at some crazy high level. Okay, but NASA's budget is less than 0.5% of the US federal budget. It's actually not very big at all. So American consumers spent more money on pet supplies last year than we spent on NASA. So if you think about things in context, okay, we live in a solar system, right? We're a planet that's going around a star. And there's rocks flying by all over the place. And we don't know where they all are. So it's not crazy to think that something bad might happen. We don't want anything bad to happen. But it would be good to try to prevent that if we could. So, and people are thinking hard about it. There's other ideas that people have had about doing this. So another idea is you have a spacecraft, you channel solar energy, and then you focus that energy via some kind of laser beam at the asteroid. And then you effectively evaporate it. So if you have enough time, you basically laser zap the thing So there's sort of all kinds of ideas floating around that people have about what you can do to these things. But people think about it because you obviously don't want something like that hitting. Yeah.
The first idea was to latch something onto the asteroid.
Yeah.
Have they thought of like space travel by latching onto asteroids?
Well, I mean, we have latched robots onto asteroids, and there's discussion of actually sending manned mission to asteroids to land on asteroids.
Yeah, because then you don't need fuel.
Right. Yeah. That's right. So yeah, you could, and what you're envisioning is, you hitch a ride on a comet that then takes you right out to Pluto or something, and then you go investigate Pluto. Then you got to get back somehow. But yeah, that's an interesting idea to think about. Yeah. So anyway, I think I'm done. If there are no more questions, I'll let you go. All right. Thank you.